first the even. So I consider a basis for G, the algebra, homogeneous. So I take first the even element, then the odd element. There is no reason to do this, because one could take first the odd or could take them mixed. It's not important. But you have to take them homogeneous. We take them like this because it's more convenient. And we also take an ordered basis. So every element is, you know which one is first, second, and so on. First, all even and odd. Then I claim that I can produce a basis for UG. Is the following. You need one. One you need because you need the scalars, so this is necessary. And then you take this map J that gives the image of G inside the UG. So it's so let's what do I write? Say IR, and then I do J. Change index, no, IR plus 1. So I take the elements I1 less or equal to IR between 1 and M. So a basis consists of products of even elements. Maybe these even elements are repeated. So these are elements in G, right? So they come from G, each of them. And maybe I repeat. So I could have, say, JX1, JX1, so I can have JX1 repeated many times. But then the odd elements, no, I don't have them repeated. So it is 1 less than IR plus 1 less than IR plus S. This goes from M plus 1 to M plus N. Okay. These are not repeated. Why is it so? Because, okay. Let us reason on the statement. So this is a basis for UG. I was thinking maybe give an example of this to see what is the deal.
Okay.
Huh?
What formula?
Yes.
Shouldn't that n plus n be n?
N plus n? Yes, I forgot the index. Here I forgot M. Here? Yes, of course. Obviously. No, so this theorem should appear evident, is however very difficult to show. It requires some care, but let us first understand why it is obvious. Do we understand it? First we must, so it is one of these deceiving theorems that seems really obvious. Let us do the example of SL2 because it's, I want to show why it is obvious. So we look at SL2C. It is generated by 3 elements. I remind you the relations. I do SL2 because if I could do the super algebra example, but then I try to explain why making the super algebra example is more difficult. But let's do this example first. So I take a basis ordered like this. Maybe you like
H 2x and
2x. Yes,
hy is minus 2y.
sorry, I was thinking about no, I was thinking about the wrong thing. Thank you. Okay, so let's order this way. Now, what happens is that suppose we have something like this. This is allow me not to write the tensor here to save time. I don't write, so I should write the tensor here, okay? But I don't write it because it is time consuming. So this is in SL2. Now, what this theorem says is that this is a basis, okay? Which means that any element that is not in this form can be written as linear combination of elements in this form. What do? I have to reorder this. So for example, let us say I reorder first h, which is simpler, so it is y, and then here I write hx. So this, oh god, it's the other way around. So this hx minus 2x. So I use this relation, right? It says hx minus xh equal to x. So I'm using this relation to write, you see what I'm doing? Okay. Then I have y hx minus 2yx. Okay, great. Then I reorder this. So this becomes hy minus 2y. I'm using this relation, there is a minus here. Then no, it's a plus because I take it the other way. Okay, x. And then I have minus 2. Now it erases, but it's just a case that it erases. Sorry, this goes away with this, but it's just a chance of this relation. Usually it will not go away. Okay, I erase this with this. Then I get hyx equal to hxy, and then I have to write minus, this is plus, right? No, minus h squared. Okay? Now those that know about Poincare-Berkovic, which is 1, 2, and 3, be silent, the others. Now it is clear that if we have this relation, we can reorder, right? It is very obvious we can reorder. So what is the problem with this theorem? I mean, it's obvious what I did. I mean, one can switch, and the proof starts with that. The proof starts showing that you can reorder. It's just a little induction on the tensor, your tensor of a degree, z degree n, and you show that you can lower the number of switches and so on, and then a simple induction. Each of us could do it. But then, what is the big deal? What is the problem?
Linear independence.
Yes, but in this example, what is... it is linear independence, in fact. It's a way of saying it. But, so, how do you see it in this example? Certainly what you say is true. If you show you can reorder, you just show they generate, then linear independence is missing. But essentially the problem is that it matters the order in which you are doing the switching, right? Because here we made a choice. We decided to switch first this, but why? We could start switching those first. Are we sure we get the same? Okay. This is the big problem in the Poincare-Berkovic. And the really surprising part is that here, you see, in doing the switching, we're just using definition of bracket. We never use Jacobi identity, and the Jacobi identity is essential to show that no matter how you reorder, which one you decide to do first, the Jacobi will tell you that you get the same result. So something that seems obvious is not obvious at all, and actually it is false if the Jacobi is not holding it. So the Jacobi identity is key to this. For the linear, and Lorenzo is right, I mean, it's linear independence the point of this. But it's the order, the way you show the linear dependence is you show that no, doesn't matter how you reorder. And the proof for the super is the same as the proof for the usual case. And the only thing is that every time you switch you have to take a sign. That's all. You have only to keep track of the minus that can appear, that's all, but it's really the same. Why did not I do this, the case of super here to show? The problem is that there is a phenomenon which appears in the super. This is open to everybody. No, but Stephen knows. See here, why do we get equal here and not equal here? What is the point of not equal? You see, there is a difference. Because I say, the proof is the same, okay, but that is strange because the statement is not the same. In the even case, I'm allowed to repeat. In the other case, no. I have only degree 1 each. So what is the point? I mean, why do I get degree of? Why don't I get the
because if you have the two odd elements.
Because if you have 2 odd elements, the bracket will be even. So I can never have h squared. See, for even element, I can have an element squared. But if I have like, say, if I have an odd x, so you remember that for the bracket of an odd element, it is x times x plus x times x. So it is 2x squared, and this is even. So the even odd that do not exist, they become, so if you multiply 2 odd elements, it becomes even, so it disappears. It is rewritten in terms of the... So why didn't I do this example? Because the simplest example which is similar to SL2 is GL11, which is generated by 4 elements, GL11, but will not display this phenomenon. In GL11, the square of an odd element is 0, the bracket. The first superalgebra having this phenomenon is OSP1, 2, which has 3 plus 2 is 5 generators. And the relations are not complicated but a bit involved. So to show the example, it will become more complicated. But you can try to reorder in OSP, and you will see that when you switch, when you add the square, it will disappear. So it's... So let's have the vote. Do we want to see the proof of Poincaré Virgo with? Certainly Fabrizio, no. It's the same. No, for me it's very easy. Very easy to prepare because I know it. I mean, I know it ridiculously, like I get confused on the grading like today, but I know it very well.
It's not just a number, right?
So
they should decide.
Maybe we could not, I don't know. What do you think, Fabrizio, is your opinion, whether we want to do it or not?
I don't know. How long does it take? Maybe 1 hour. It's not
It's not smart.
Not
No, well, it's very smart. No, it's very smart, but it's not. I did on the first thought.
I think it's an important proof. So maybe
No, it's a very important proof, but I'm not sure that one needs it. That's the thing. It gives you a first glimpse that this theory is not so obvious as it seems, but
it's something that they can learn.
Huh?
It's something which is important so that they can learn it. I think it's worth doing for them.
Yeah, but the seminar is also for us. For us, it's boring. No, I'm glad if I do it because then I don't have to prepare, so it will be like today that I wrote
You
the
can probably do a sketch of the proof. And the main
A
steps.
sketch I could do now. I mean, I know it by hand. I know it by heart. I will do a mess because I didn't even read it. So I will do a disaster. Okay, let's do it a sketch next time. But the sketch I already did, right? There is this. There are two problems: the generation that is done with an induction on the degree that you know. Huh?
You already done it.
Yes, and then the key point is the key point is showing that when you do the switches, let's do the sketch on the switches I can do because, but maybe it would be nice to reread it once before doing this, but okay. So let's keep the basis, okay. So the point is the following. You have to show it then, when you reorder the terms, you get a no ambiguity. So if you have so you get some point here. So suppose that you have two things that you can. So first of all, the induction that you did in the first part was done on the number, help me Fabrizio, what is called the number of disordered pair, which is the length of the permutation, right? The number, so your basis means that it should be ordered, right? So the induction where you prove that this is a generators, it is done on the number of indices which are exchanged, so they're not ordered. So this, at this point, suppose that you have two things that are like this. It is kind of stupid right like this, sorry. So let's write I1, and here I say K, IK plus 1, and similar here, K, J, sorry, I, J, because I use the other. So this is the situation, right? So this means that this index is greater than this in the order. So you have two possibilities. It is clear that if these two are disjoint, it doesn't matter at all whether you do the switch this or the switch here. You can do the other. So the only point that is important in when there is overlapping, what is called overlapping ambiguity. So switching this first and then this or vice versa, it doesn't matter, because they're separated. The only thing that matters is when you have a situation like this, what is called the overlapping ambiguity. Now, what you do, you switch first this, and you add something, and then you switch this. So you do like here, essentially, because this is really what amounts, right? This is the situation. So you do the switches. If you do them, you have some terms coming more, the brackets. And these brackets, so what you do is the following. So you have like, very quickly, so you reorder. So you do like first way. You reorder first this, you do the one type of reordering, and then you have a second way of reordering. And you get an expression, and this expression will cancel. What remains is the Jacobi identity. You will get the Jacobi identity, which is 0. So it's very nice. Especially because at first glance it seems obvious, but it's not. So I think this is the original proof of the Poincaré-Pescovic. But there is a modern proof by Bergman, which is the diamond lemma. It proves in a modern way, but a modern way I don't like. So there is this is the original. This is something called the diamond lemma. And now if you take a book, they will prove it with diamond lemma because it's the modern one. A diamond lemma is more, what can I say, is more general. Diamond lemma tells if you have to reorder something which is not the Poincaré-Bergouin theorem. So something, you have relations, you have words, it's way more general. And this is by Bergman. But I prefer this because this is like, we need this, so we do this. I don't know, Fabrizio, this is a very poor sketch.
No.
Basta. So today I wanted to speak about the Classica and I have to go. I'm sorry, very boring.
In this proof, you are using implicitly the this word theorem.
What? The
This word theorem.
what is?
Because you have a permutation of the elements,
Yes.
and you want to put them in the right order.
Yes.
And then you say that there are many ways to do this.
Yes.
And so it amounts to a permutation and to two expressions for this permutation as a product of
Transposition.
elementary transposition.
Yes. Yes. Of course I'm using this. Yes.
Yeah. And you're using the fact that, but not only this, you're using that to pass from one to another, you can do the simple
Yes.
moves.
Yes. Yes. You lose more. The fact that you reduce the length.
You can just compare these elementary things.
Yes, I'm using many elementary facts on the permutation group.
And this is not elementary, this is a theorem of Kitz.
No, I don't think you need the full blast of theorem. I mean, if you reorder a pair, the number of disordered pair will be lower than one, right? I mean, no?
No, you are using that SI plus 1, SI is equal to SI plus 1, SI plus 1, and performing these operations, you can pass from one reduced expression to another. So a reduced expression is a way to perform this
Yeah, I'm not
operations.
sure that you need this theorem, I'm not sure. You need just to know a few things about permutation, not... But I did not even read it, I mean, this thing before coming here. I mean, I just remember from very far. Because this proof you don't really need to do stuff, I mean, it's not...
Yeah, and then I'm not convinced that this is enough.
Next.
Because you didn't show the linear independence.
No, I didn't show the linear independence. No, you're right. I did. This is like a very gappy proof. It's not a proof. I just explained the tricks that are here and there. No.
Once you know this, you know that at the end you arrive to the...
This is not a proof. Poincaré-Bergouin is...
But there is something more. I mean,
facciamo che vengo. Next time I come and give it... No, because I think you don't need anything about permutations. But we'll have a challenge. I come here. Non lo so.
No, vabbè, okay.
No, Poincaré-Bergouin is very important. I remember Varadarajan made me study it a lot. Like I spent a long time on it, very long time. It's the categorical proof. Right, Stephen is very obsessed with Poincaré-Bergouin.
Yes, I would say so.
So it is not the time which is wasted, I think. But on the other hand, I was afraid that it would be boring for you. But if you seem excited by seeing the proof, then it will be... No, non lo so. You let me know. You don't have to let me know now, but... For me it's easier, because then I don't prepare. I just look quickly, it's simpler.